Hello everyone! Today's video is about Bell's inequalities. This is planet Earth and the two circles on it represent two qubits. The two lines inside each qubit representation correspond to the two possible states, ket 0 and ket 1. We let these two qubits interact and their states become entangled with each other. Then we keep one qubit on Earth and send the second one far away, placing it on a planet 50 million light years away. Say that this is the ket that represents the two-qubit state, with the first qubit being on Earth and the second one being on the faraway planet. If qubit 1 is measured and we find that its state was rendered into ket 0, immediately and not 50 million years later, qubit 2 will be rendered into ket 1. Similarly, if qubit 1 after measurement is in ket 1, qubit 2 will be in ket 0. This is a very strong correlation. Moreover, not only is this correlation observed in the computational basis ket 0 and ket 1, but in other bases. For example, if we express the state in this diagonal basis ket plus and ket minus, we get this. Similar strong correlation observed. If qubit 1 is in the plus state, qubit 2 will be in the minus state, and so on. What quantum theory is telling us is that measuring qubit 1 instantaneously affects qubit 2. But how is that possible when we know information cannot travel faster than the speed of light? Quantum theory is essentially advocating the spooky action at a distance view. Or could it be that the theory is just incomplete, and if we complete it by including the missing variables, all the measurement results will be predetermined and no spookiness observed? Could these hidden variables really exist? How can we test that? Well, that's what Bell's inequalities are all about. Before we get into that, I'd like to make a comment. Bell's inequalities are not universal relations or laws that apply in all situations, as Newton's second law does, for example. In the latter case, force always equals mass times acceleration, or the acceleration is always directly proportional to the net force and inversely proportional to its mass. In the case of Bell inequalities, you can set up your own Bell inequality depending on the experimental setup and what correlations you want to focus on, while sticking to certain guidelines. Today, we'll look at one called the CHSH inequality. Here's how to set it up. For each of the two qubits, choose two operators, each of which can take only two values, plus or minus 1. A and B for qubit 1, C and D for qubit 2. Then, with simple mathematical reasoning, the inequality S can be derived assuming hidden variables exist. The variables in the inequality, which are functions of the alleged hidden variables, correspond to the measurement outcomes of the operators, and the bar over the products correspond to the average. For our two-qubit state, by choosing the values that optimize S and using quantum theory, we get S equals 2 times the square root of 2, in clear violation of the inequality. Therefore, a hidden variable description is not compatible with the predictions of quantum mechanics, and we have to drop it. Why do we choose to stick to quantum mechanics? Well, its predictions agree with experimental observations so far, so we choose to accept it and put up with its weirdness. It's exercise time. You need to derive the CHSH inequality that we discussed on the previous slide. First, in part A, use the fact that the operators A, B, C, and D can only take two values, plus or minus 1, to show that the absolute value of A times C plus B times C plus A times D minus B times D equals 2. Then take the average of the whole thing. Then, in part B, use a mathematical trick to get this inequality. Here's a hint to the trick. If I give you a bunch of negative and positive numbers and ask you to calculate the average, then take the absolute value of that. How will the answer compare to first taking the absolute value of the numbers and then calculating the average? Ciao!